So here's the first place where it might seem like I'm not actually using that rule, but totally are. By the way, here's the official way to write the rule I just said earlier. If the function is written as x to some power, then the derivative can be found by multiplying the power and the coefficient together. That makes the new coefficient. So that's the way we just describe mathematically that we've taken the power times the coefficient. And then whatever that power was gets decreased by 1. So this is the kind of thing you're going to see a lot, moving forward in like the front of textbooks and things like that. People are like, hey, this is the power. This is called the power rule for derivatives. Now, if you're not seeing how it connects here, we just need to think about the fact that this rule works if it's x to a power, not x in the denominator. That's not the same thing. I'm not reading this as an x squared or an x or an x cubed. I mean, these are x's to a power, but they are not written in this form where it's x to a power and that x is in the numerator. It does need to be in the numerator of the function for this rule to work. So maybe you can think about other ways you've been taught to express these ideas. And when you think about that and realize that, you will see that that rule completely is still in full effect. It's interesting because it does ask you guys to break a rule, something that you had drilled into your heads as younger students, where your teacher was always like, minus half a point because you didn't blah, blah, blah. But now we actually want you to not do the blah, blah, blah anymore. And if you don't know what the blah, blah, blah is, I'll just for a moment ask you to consider negative exponents and what you know about negative exponents. And then pause for a moment, contemplate negative exponents with these yellow functions, and then see if you can understand how that rule that I've got here in beautiful gray is still in full effect. So go ahead and pause and think about that now. And now that I assume you've unpaused, or whatever, maybe you already see the what's going on, we are going to have to rethink about all of these functions as not 1 over x squared, but as x to a power. These are equivalent expressions. This can be thought of as x to the negative 1 power. I can think of this as being x to the negative 3, this as being x to the negative 4, and you've had it beat into your heads to not use negative exponents, but in calculus they're actually very helpful. And I will often say, think about it in terms of negative exponents, and that's what happens. And if you're still not quite seeing how, therefore, that makes these derivatives over here, correct, just think about, we'll look at this guy right here, and I'll do him down here in beautiful light blue. If w of x, if I think of it as x to the negative 2, we'll set a 1 in front of this, because it's helpful to think of the coefficient that's there, then the rule for the derivative is to take the power times the coefficient to get the new coefficient. So I'm doing negative 2 times 1 is negative 2. And then I'll decrease this power by 1. So if I have negative 2 and I subtract a 1, I will get a negative 3. Now, honestly, if you're in a calc class, your teacher will be pleased as punch if you leave your answer just like this. But if you actually have to evaluate it and plug x's in, it's usually more helpful to use what you had beat in your head so much beforehand, which is to have this be not negative exponents. So it is usually a better idea to think of it as negative 2 over x to the 3rd. Just because, I will say most kids, if you ask them to raise, like if I had, for instance, an x value of, say, 5, taking negative 2 over 5 to the 3rd makes more sense to most people in the world than taking negative 2 times 5 to the negative 3 power. People kind of get confused about what that means. You don't have to do it. You don't have to convert it to this format. Honestly, since you're all going on to calculus, I assume you should be well adept in understanding that these two ideas are interchangeable. But for now, just whatever you're most comfortable with is fine with me. As you look at the rest of these examples, hopefully you can see how this rule is in play. And we just have one more thing to look at that wasn't obvious at all. And we'll call it good. Yeah, one more slide. Let's do this.